Hello, welcome back. We are going to be picking up the rest of chapter 4 today. Alright, so we're getting into this thing called hypothesis testing. And maybe the best example I can start this off with, if you remember from last week, we had looked at something like this. We had just kind of been given this information that maybe um, Coke claims 300 milliliters are in every single bottle. And we worked it out. We found a confidence interval. I guess this must have been 99% confidence interval um, based off of our sample. So we took a point estimate. Our point estimate was 298.4, and it had we knew that the population standard deviation was 4.2. So we were going to kind of compare this to see if there is actually 300 milliliters in this bottle of Coke. Well, what we find is we have this confidence interval, but we don't see 300 in this interval, right? It's out just to the right of this thing. So because 300 is not in this interval, what that means is it's enough for us to say that yes, this is significantly different, so that we could go ahead and say yes, Coke is not giving us 300 milliliters. So that's one way to do it with confidence intervals. However, what we'll be looking into today is setting up this thing called a hypothesis test and using the p-value method to evaluate this. So there's two parts in a hypothesis test. There's this HO. This is called the null hypothesis. And then there's the HA, which is called the alternative hypothesis. So just to give you an idea, HO is always going to have an equal sign. So when we set any of our hypotheses up, they're always going to look like this. HO something equals something, and HA we gotta have less than, not equal to, or greater than. So anything except for an equal sign. So in this kind of situation, we were looking at the actual mean that Coke puts in the bottle. So we were testing the volume mean. So our point estimate was x bar, but we're going to go ahead and use the population mean here. So the null hypothesis, the way this works, you go ahead and assume that it's true. So we'll go ahead and assume that Coke does give us 300. And the alternative is what? The population parameter, mu, is not equal to 300. So this basically covers all of our bases. And this is just setting up the hypothesis. We're not going to run through it just yet, just to get familiar with how to set these things up. Alright? Your book kind of goes through this idea, or this one example, I suppose, on page 172. They tell us that the difference in running times for men and women, this is men minus women, this point estimate that we found is 6.82. And we had a standard error of 3.05. So suppose we were asked to test whether or not the difference between men and women, if there was a difference. So maybe we're asked, is there any significant difference, right? We know that if we have a bunch of different samples, if they're not different, you know, the men might run a little faster in this marathon, women might run a little faster in this marathon, and so it's expected to change a little bit, but we're talking about significant difference or statistical significant difference. Let's go ahead and set this up. So we'll need HO and HA. Again, this is our null hypothesis. This is our alternative hypothesis. So before we begin, what are we looking at? We're looking at the mean, right? So what's the population parameter for the mean? It's mu. So I'm going to have mu. And HO, I already know I'm going to have mu equal something. Okay. So if there is no difference, when I subtract their averages, what do I get? They should be the same. So when I subtract them, I should get 0. That means no difference, right? If there is a difference, then it's not going to equal 0. So this would be how we would set this hypothesis up. Just getting a little more familiar with this. Of course, we can have other types of parameters. So we haven't talked about it yet. We'll get to it in chapter 5. But we denote P as a proportion. Just like we denote mu as our mean. And so we're told that the proportion of men, so proportion of men, in our race, we found that to be 0.48, or 48% of them were men. And we had a standard error of 0.05. Don't worry too much about these carets on top of the p. This just means the point estimate for this. The point estimate for mu was x bar. The point estimate for p is p hat. So we're not going to go into how to find the standard error yet, but we're just told that the proportion of men is 0.48, and it has a standard error of 0.05. Okay, so again, if we were going to set this up, perhaps we're interested to see if the proportion of men is actually 50%. So of course right here, it's a little bit lower, but we might be inclined to think, well, sure, it might be actually 50%, it's just a little low. Okay, so if we were going to test that out, we'd have our HO, we'd have our HA, and we'd have, and this time, the population parameter is P, so we have P equals 0.5, it's actually half and half, and P is not equal to 0.5. So it's fairly simple to set this thing up. Suppose we were interested in setting up a confidence interval for this. So maybe we were going to set up a 90% confidence interval. Just recall, for a confidence interval, we use the point estimate plus or minus z star of alpha over 2 times the standard error of our point estimate. So the point estimate here is 0.48 plus or minus z star of alpha over 2. Let's see. If we're confident of 90%, that means the complement of that is our alpha or significance level. That means it must be 0.1 minus 0.9 gives us 0.1. So we're looking for a z star of 0.05. And if you do recall, I had you write down these last time. So you should already know z of alpha over 2 star is going to be 1.645. Of course, we know how to use the chart to get it anyhow. And then we're told that the standard error of this point estimate is 0.05. So just filling this in, we saw there was 1.645 times 0.05. If we multiply this all out, we should find our confidence interval is 0.3975, comma 0.5625. So what could we conclude based off of our confidence interval? Well, we were testing, or we were interested to see if the actual proportion of men was 50%, or 0.5. Do we have 0.5 in this interval? We certainly do. So because 0.5 is in this interval, it seems a good possibility that indeed the proportion of men could be 50%. That means we cannot say with significant, statistical significant difference between 0.48 and 0.5 here for the men. And don't worry, we'll get more into these proportions in chapter 5. So the rest of chapter 4, you won't be actually computing any of this stuff. Okay, I think now might be a good idea to go ahead and get into the idea of these p-values. So we've used z-scores in the past. It's nothing than what you observe, or your point estimate. Here it's going to look a little bit different when we do it in the hypothesis. It's going to be the point estimate minus the null value. And I'll explain what I mean by that in a second. All divided by the standard error of our point estimate. So let's go ahead and just say our point estimate was 0.025. Our null value maybe 0. And our standard error is maybe 0.013. If this is what we have, then we find our z is 1.92. Okay. So 1.92 is approximately here. The p-value is going to be, it's going to depend on how many tails you have. Let's focus first on a one-tailed p-value. So a one-tailed p-value is as simple as you find 1.92, and then you find the area underneath this normal curve, the standard normal curve that lies above 1.92. So this turns out, if you do look this up, it should give you 0.027. So the p-value is this area above it. So that would be a one-sided p-value. Alright. We could also have a two-sided p-value, which is something that looks like this. If we have a two-sided p-value, let's say we found that z was let's go ahead and say it was 2. Then this would be 0 here, negative 2 here, and positive 2 there. So the p-value for two-sided would be these areas. So what you would do is you would find this area, and you could find this area as well and add them together, but what you'll find out is actually much, much easier to just assume or use the assumption that this is symmetric, and then we only have to look one of these things up. So if you look it up, the area should be 0.0228. This area should be 0.0228. So this area must also be 0.0228. And so the total area here, you add these things up, and you do get 0.0456. Okay, so more on the hypothesis testing and the p-value. All right. So when we're testing something, the way we test it is we test it at a significance level or a confidence level. It's going to look very similar to our confidence interval, meaning that if we're testing something at 90% confidence, that means our alpha is 0.1. And what we do is we compare our p-value to this alpha, and we make our decision based on that. Okay, so how do we know if we're in one-sided or two-sided? So we have HO, we have HA. We have something equals something up here. If I have this tells me I have a two-sided p-value. Two-sided test or a two-sided p-value. Which means whatever that area you find, you have to double it because there are two sides, two tails there, and they're equal size. Okay? Now, of course, the other option is that you're always going to have an equal sign here, but HA, we could have a greater than, or we could have a less than. If we have one of these things, it means it's only to one side, and then we have a one-sided test. And thus a one-sided p-value. Okay, let's look at the decisions here. Once we find our p-value, we're going to go ahead and make a decision. And let me go ahead and just draw out the actual steps that will be involved here. So during a hypothesis test, the first step is write your hypothesis. So this means your HO, your HA. Write these things out. Your second step is go ahead and use your point estimate to find your z-score. The third step is to find the p-value. So the p-value is going to depend again on what's up here. You of course have an equal sign for the HO, but if you have a not equal sign, you have a two-sided p-value. If you have a greater than, one-sided p-value. If you have a less than, also one-sided p-value. So you use this z-score to find your p-value based off the standard normal curve. And lastly, we make a decision. So we're going to compare alpha. So, actually I'll write it this way. If our p-value is small, meaning it's smaller than our alpha, then we reject HO. If our p-value is big, bigger than alpha, we fail to reject HO. And maybe lastly, we should summarize in English what our findings are. But these are the steps that we'll actually walk through during our hypothesis testing. So let's go ahead and use these steps in an actual problem just to see what it looks like. So we are told a pizza place in New York in 2008, or I guess we were looking at average pizza places in New York. The average pizza places in New York For a slice, it would run you $2.42. So this was the old time. Alright. In 2011, we'd like to see if it's changed. Or I guess it's 13 now. We can be current. 2013, we want to test at 95% confidence to see if the prices have changed. Okay. So in doing this, we'll go ahead and say we take a sample of 50 in 2013, and we find that the average price, or X bar here, is $2.53. And we had a standard deviation of 48 cents. 48 cents. Okay. So that's the problem. Let's go ahead and work through the steps. So first things first, we want to go ahead and write our hypothesis, HO and HA. Okay, so let's do that. HO, what do we have? What are we talking about? We're talking about averages in the whole state of New York. So we're talking about averages, so we're talking about means. So we think, what's the population parameter of mean? It's going to be mu. So we'll have mu equals for HO. For HA, we've got mu. Well, we have to decide. We have to put some numbers in here. Okay, so let's see. HO is assumed that nothing happens, that it's the same. That's always the case. So let's see. We have 95% confidence that the prices have changed. If the prices have not changed, then it's actually $2.42. So we put this $2.42 in there. And what that means is we're testing to see if maybe we got a larger value here, but maybe that's just because we happen to sample 50 of the more pricier pizza joints in New York. You know, maybe more in New York City or something like that. Maybe it wasn't a very good random sample. So we'd like to test with some significance if this is true or not. And of course, we just want to see if it's changed. So changed, it could change up or it could change down. So I don't know which way it's changing. So all I can say is that it's not going to be equal. Of course, if I said instead 95% confidence test to see if the prices have increased, then I would put greater than here, because that would mean that these prices must be greater than the old 242. If I said decreased, then I'd have to put less than. So here I've just said changed, so I put not equal to. So we've got our hypothesis test. The next thing we want to do is find our z-score. So did number one, let's find our z-score using our point estimate. So I'll scoot this up just a tad. Okay, so the z-score for hypothesis testing is going to be our point estimate minus our null value, all divided by the standard error of our point estimate. Okay, so what does this give us? Our point estimate is what? X bar, it's this $2.53. The null value, here's where I'm going to explain this. The null value comes from the null hypothesis. So we look at the null hypothesis, we see that it was $2.42. So whatever's on the other side of this equal sign, that's your null value here. So we'll fill that in as minus 242, all divided by the standard error of this point estimate. But our point estimate is X bar, so it's actually the standard error of this X bar. So remember what that means for us. It's actually going to be what? The standard deviation divided by the square root of n. So that's actually our standard error here. Okay, so let's go ahead and fill that in. We have all the information. It's going to be 2.53 minus 2.42, all divided by, we had 48 cents as our standard deviation. So 0.48, we're talking about dollars here, so it makes sense to go ahead and change the cents to dollars. And divided by, we had 50, so over the square root of 50. So let's go ahead and compute these things. If you do the top, you should come up with 0.11. And if you do the bottom, you should come out with 0.06788, something along those lines. And so dividing this out, we should get about 1.62. This is different from Z star, right? So our Z score is 1.62. So we've done that. Now we have to find the p-value. So first of all, before we do, let's decide, are we doing a one-sided p-value or a two-sided p-value? To do that, we do have to look back at our hypothesis. And all I care about is looking at this. So this not equal, I could be to the right of this thing, I could be above it, or I could be below it. So I've got two tails here. This makes this a two-sided p-value. So what that means is, because it's two-sided, I'll actually be interested in the positive and negative of this thing. So to sort of draw this thing out for you, we found 1.62. Remember, we've standardized this, so we could miss this to the right by 1.62. We could also miss it to the left by 1.62. So this is why I actually want both the positive and the negative. So I have the two-sided p-value. Let's go ahead and look in our chart to see what this area is. Looking in the back, we open up and we find negative 1.6, 0.2. This should be 0.0526. And so without even looking for the other one, I know that this is also 0.0526. And so my total p-value, because it's two-sided, is going to be twice this value. So you could either do 2 times this, or you could add both of these together. Either way, you should come out with 0.1052. So we found our p-value. That. So we've done our hypothesis. We used our point estimate to find our z-score. We've now found our p-value. We now have to make a decision. Okay. So let's see. We have to find our alpha. We were told originally to do what? We were told to do a 95% confidence interval. So if we're 95% confident, means we were 95% confident. That's essentially 0.95. So our alpha is actually 1 minus 0.95. Our alpha is 0.05. So let's compare this. Okay, so our alpha, or 0.05, is actually less than our p-value. 0.1052. So this means our p-value is large. Our p-value is larger than alpha. Actually, let me go ahead and, let me put the p-value on the other side. It doesn't really matter. We still come to the same conclusion. P-value is larger than alpha. So what do we say when that happens? When the p-value is large, we fail to reject HO. So what we can conclude is that we fail to reject HO. Okay, so what does that mean in English? You should, of course, think about what that means. Go back a few pages. So we're looking at the pizza prices. How have they changed in the last 5 years? So we did this sample, and we tested it. Failing to reject HO means that we cannot throw this away. So it might be true. It might be false, but we don't have enough evidence to say that it's false. So we cannot conclude that the prices have changed. And that's really ultimately what our final summary is. There is not sufficient or enough evidence to show the prices differ. Again, we're talking about statistical significance here. Of course, the prices differ. This one's 253, this one's 242, but we're talking about this projection to the actual population. Okay, so that's a nice example, just working that one out. If you do find the confidence interval for this, you can do it at home. Let's say I did a 95% confidence interval for this. I'll just tell you what I got. 2.397 and 2.663. What you notice is that 2.42 is actually inside this interval. And so, because it's inside of there, we would fail to reject it because it seems like it's a possibility. It's inside this interval. These were the extremes at 95%. So it's in there, so 95% might be true. Okay, so I'll go ahead and make the point now. It's not, they're not exactly the same thing. Confidence tests, or hypothesis testing, and confidence intervals. If they are two-sided, meaning we have non-equal, then essentially it's the same thing. You can do it this way. If the point is in there, then you fail to reject. If the point is not in there, then you reject HO. If we had rejected HO, it just means that we would reject this, throw this out, and say, aha, this means this is true, which means that the prices differ. Let's do one more real quick, and then we'll move on. Let's see if I can make something up real quick. Okay, so we'll use another kind of Coke Pepsi thing. Pepsi claims to have 50% of the sugar than Coke. And Coke has 300 grams of sugar. Well, that seems a little high. Let's go with 60 grams of sugar in one can. Okay, so Pepsi is claiming they have 50% of this, and we're going to go ahead and test this. at 90%, that Pepsi has more sugar than this. Okay. And in the process, we do find out that, let's say we sample 64 Pepsis, and we do all of the tests, and chemist helps us out, and we find that there's an average of, let's say, 30.9 grams of sugar, and we find that the standard deviation between these actual 64 is actually 3.4 grams. Okay, so this is our test. So first things first, we do have to write the hypothesis, right? Okay, I lost my sheet. I'll have to do it from memory. Oh, maybe. So to do our hypothesis, so we want to write this thing down. We have HO, we have HA. Let's go ahead and figure it out. Of course, we have some kind of equal sign here. And what goes here is the population parameters. So what are we talking about here? We're talking about averages, right? We took a sample of 64, we found some averages to see if the population average of these Pepsis is actually doing what they're saying. So average means mean, so we're talking about mu. So we've got mu's here. Okay. So we say Pepsi claims to have 50% of the sugar. What goes up here is you assume that this is true, that there is no difference, right? So 50% of 60 grams gives us 30 grams, right? And our mu, if we read this closely, what are we testing? We're testing that Pepsi actually has more sugar than they claim. Well, if they have more sugar than they claim, then it should actually be more than 30. So this is one of these things where we're not saying it can be more, it could be less, that would be not equal. Now we have greater than. So this is actually going to be a one-sided test, or one-sided p-value. Let's go ahead and get some of this other stuff out of the way. If our confidence is 90%, that means our alpha is 0.1. So we already know what our alpha is. It's going to be 1 minus 0.9, because this is 0.1. And we have this information to go off of to find the next thing. We need to use our point estimates to find our z-score. So recall our z-score is just the point estimate minus the null value, all divided by the standard error of the point estimate. So what this gives us, our point estimate here is, again, this is just what we observed. This is what our sample gave us. This is what we were testing. The testing is 30.9 minus the null value. So the null value is right here. It comes from here. We've got this 30 here. So this is 30.9 minus 30 divided by what? The standard error of this point estimate. So again, we have the standard error of x bar, which is the standard deviation, population standard deviation, divided by the square root of n. And we have both of these things. We have standard deviation is 3.4, n is 64. Okay, so let's go ahead and fill this in. It's going to be 30.9 minus 30 divided by 3.4 divided by the square root of 64. So on the top we should get 0.9. On the bottom we have 3.4 divided by 8. Let's see what that gives us. This is 0.9 divided by 0.425. Or 2.117 or 118. So again, because we're using our table, we're going to go ahead and round this actually. Instead of to this, let me round it to the nearest hundred, so that way you can find it in our table. So let's round it to 2.12. Okay, so let's go on to the next thing. We have to find the p-value next. So we did these first two, find the p-value. What kind of p-value is it? Well, we go up here, we look at this thing, our HA. Doesn't matter anything else about it, just whether or not we have a not equal sign or not. So because we just have a greater than, we can only miss this above it, things that are greater than this. So this is a one-sided p-value. So we don't have this thing going on, just missing it above it. So to draw this thing out, it's going to be a little bit above this thing. We're interested in the area that lies above it. So this is the one-sided p-value. Let's go ahead and use our book to find that. Instead of looking up positive 2.12, I will be looking up negative 2.12 because these things are symmetrical. And I don't have to do anything complicated to find out what my area is. Okay, so 2.12 gives us an area of 0.017. But that's it, right? There is no other side of this, so I don't have to times this by 2 or anything. My p-value is just equal to this value. Okay, so the last thing to do, I do have to compare this p-value to my significance level. So my significance level, if you recall, we were doing a 90% test. So we had our alpha is 0.1. So my p-value, 0.017, compared to 0.1, it's very small. It's much, much smaller. So what we do is when our p-value is small, less than alpha, we reject HO. So in this case, we will be rejecting HO. Okay, so that's our conclusion. What does that mean? Again, we're just testing to see. Pepsi says they've put less than 30 grams of sugar in their Coke. We think they're lying. We think they put more. So we're testing to see if they put more. So we reject HO, which means we throw this guy out. This is our null hypothesis. So boom, that's no good. Move to our alternative. That must be true then, right? We threw this out. So we reject HO, and what we can conclude is actually significant. We can conclude with 90% confidence that the mean here is bigger than 30, which we're just talking about the average that sugar that's in Coke. So we can say confidence that, oh, I'm sorry, Pepsi. Pepsi has more sugar than 30 grams, or really more than 50% of the Coke sugar. All right, so that's two examples for you. That's generally what we'll have you do. The rest of this chapter, you're just using X bar, so don't worry too much about that. Just kind of use X bar. It's going to be exactly like those two examples now. There's one last thing that we need to go over. This is this bit in 4.6, and this has to do with sample size. So we'd like to kind of, of course we have this method to see confidence level after we have a sample. Well, suppose we want to know ahead of time what kind of a good idea of what sample size we should do. If we do a sample of 100 and then it's like that's not narrow enough, we need to sample about 1,000 more, see what happens. Still not enough. Let's sample another 1,000. This is really time consuming. It's not nice for us. We'd like to find a method where we can get an idea of what sample size we should use before we go ahead and to prevent us from doing multiple surveys. Okay, so specifically we're going to be looking for X bar to approximate the mean. So we're looking for sample size means. Later we'll do it for proportion. Okay, so if I have the mean, again, we have the confidence level. So let's say X bar is our point estimate, plus or minus Z star of alpha over 2 times the standard error of X bar. Well, we can rewrite that as X bar plus or minus Z star of alpha over 2 times what? The population standard deviation, all divided by the square root of n. Okay, so how much is this thing off by? Well, it's missing to the right and it's missing to the left, right? Adding a little bit above this, a little bit below it. At most, the error, which we will call margin of error, and we'll write it as ME, is equal to Z star of alpha over 2 times the population standard deviation divided by square root of n. It turns out that this is really easy to solve for. I can multiply both sides by the square root of n to get this sort of thing, of alpha over 2, and I can divide both sides by ME, the margin of error. And that would give me square root of n on this side, but we do want n, so we'll go ahead and square both sides to get rid of the square root. Okay, your book does not give this to you, so if you do not see it in your book, I recommend writing it down. This is the formula that we'll be using to find the size, the number of people we need to survey to guarantee a certain margin of error at a given confidence level. So we'll go ahead and see what this looks like real quick. Okay, so at 95% confidence level, what is the fewest number of samples to find within 0.2 inches of national height? If we know that the standard deviation is 3.47. Okay, so there's a couple things here. We have this confidence level. We have within 0.2 inches, and we have standard deviation. So we want to know the sample size. So we'll use our sample size formula. It's just this thing. So we don't know n. We do have to find a couple things here. Z star of alpha over 2. We do need to know what standard deviation is and what the margin of error is. So let's go ahead and label these things. Margin of error, let's find that thing first. Alright, so how can we miss? We can only miss by 0.2 inches. So our margin of error is 0.2. Alright. Standard deviation, we'll also go ahead and assume this is in inches. Standard deviation is 3.47, right there. Z star of alpha over 2. Well, make it two parts of this. Let's make sure we have our alpha first. If 95% is our confidence level, then our alpha is going to be 1 minus 0.95, which gives us 0.05. So this would be, and again, actually, this might be just simpler if you do remember this chart. Z star of alpha over 2, when it's 95% confidence, is actually 1.96. That will help you out. Again, we often use 90%, 95%, 99%. Of course, you should know how to do it the other way as well. The other way is find this of 0.05 divided by 2, which is the star of 0.025. So you would find this inside. You find this inside of this table. You know, these areas, not these locations on the outside, but actually the areas inside. And then you read off the location there. You'd see that it's actually, if you look this up, it gives you negative 1.96. Okay, so we have all this stuff. So let's go ahead and plug it into our formula. Okay, so n is equal to, here this is 1.96 times our standard deviation, which is 3.47, all divided by 0.2, which is our margin of error, and you square this thing. So on the inside we have 1.96 times 3.47 gives us 6.8, divided by 0.2. So on the inside you should get 34.006. We want to square this thing. Okay, what we find is 1156.408, something along this line. Okay, so what do we do with this? Of course, we're not going to survey 1,156.408 people, so do we say 1,156 or do we say 1,157? We don't want to lose our confidence. If we survey less people, we're going to be less confident, right? So just to guarantee that we have this confidence, it's sort of saying, well, you need a little more than 1,156. So we actually do need to round this up to 1,157. So it's sort of weird that no matter what, you're going to take this value and round it up. So if it's that on the dot, it's 1,156. But any other time, if you have any kind of decimal at all, it's not normal rounding rules. It's just that means that you need a little bit more. So you can't survey a fraction of a person. That extra person, we count them, right? We count them as one person. Everyone's treated equally here. Okay, so what you've got, know your margin of error. Know this formula. This is not in your book. Know your hypothesis testing. This, how to find your z-scores, how to find your p-value, and how to make your decision off this, and what that decision means. And that should cover it. Alright, see you next time.